Hey everyone, this is Fatima, and in this series of mathematics for AI and ML, today we're going to have a look at automated differentiation. This video is going to be a quick introduction to what automatic differentiation is, and I'll show you some codes integrated with automated differentiation. So let's start. First of all, I would like you to tell the different names automated differentiation goes by. Let me write these names first and then we'll start this tutorial. So the names are so it is also known as autodiff for short, also autograd because it's heavily involved in calculating gradients in machine learning. Then we can also call it computational diff or reverse mode diff or algorithmic differentiation. So these are the names you will find while you're working with differentiations for mathematics. Also, automated differentiation is distinct from classical methods of differentiation like numerical differentiation, which is let me write it first. It's distinct from classical methods. Okay, so it's distinct from classical methods of differentiation like numerical differentiation, which is like if you know delta method. And the problem with trying to use the numerical method is in computational system is that it introduces rounding errors, and automated differentiation is also distinct from symbolic differentiation, which usually uses the algebraic rules. What I'm trying to say is trying to code up all these rules and applying them, these are very, very, very inefficient, especially as we move forward to complex algorithms. You will find a lot of nested functions, you will find recursions. I'm not saying your code won't work, it will work or it would work. You could write a program to do symbolic differentiation if only if it's very simple functions that you're differentiating. But as soon as you will get to the real world examples, or machine learning, in the field of machine learning, it will just not going to work out for you. And relative to classic methods, automated differentiation better handles function with many inputs. I'll write it now and then I'll explain it later. Relative to classical methods, automated differentiation better handles function with many inputs, which are very common in machine learning, as well as higher order derivatives at high level. The way that automatic differentiation works is by applying the chain rule, and it's typically the partial derivative chain rule. Moving forward, do you remember the partial derivative rule? It's let me write it first. I have a equation that most of us already knows. So this equation of the chain rule shows how if we have forward pass of equations where x allows us to compute u and u allows us to compute y, so we have this chain of two functions. From that, we can use this chain rule to multiply the derivatives of these two functions separately. Oh my god, wait. Yes. So from that we can use the chain rule to multiply the derivatives of the two functions separately and obtain the derivative of y respect to x. So this is a quick refresh of the chain rule. And whereas the chain rule when we used it by hand, we typically begin at the most nested function, the innermost function, whereas autodiff typically proceeds from the outermost function inward, or always, actually not typically, it always proceeds from the outermost function inward. And this is why it's sometimes called reverse mode differentiation. And let me write. Automatic differentiation is a really computationally convenient approach. It has only a small constant factor, more computational complexity than the forward pass itself. So if the forward pass if the forward pass allows us to go from x to u, so if the forward pass allows us goes from x to u, then from u to y, that in that chain of two functions, then automatic differentiation backwards from y through x, that allows us to calculate the derivative of y with respect to x, is only a tiny constant amount of more computationally expensive relative to the forward pass itself, the initial forward pass. So that gives you a sense of what automatic differentiation is at a high level. And now we are going to apply autodiff in code. And we'll see autodiff in action in both PyTorch and TensorFlow. We can use these automatic differentiation libraries like TensorFlow and PyTorch to perform derivative calculus, and this comes in handy in a broad range of problems, particularly machine learning problems, but you could potentially use them even more broadly for other kinds of calculus problems. So we think of TensorFlow and PyTorch as being deep learning libraries. Typically, most people who know them think of them as a deep learning libraries, but they're much broader than that. They have much more applicability than to just neural networks. So why not just use both of these libraries to calculate the derivative of this function here, where y is equal to x squared, and specifically we're going to calculate the slope of this curve y equals to x squared at the point where x is equal to 5. And we could use the derivative rules that we learned previously. So y equals to x squared according to the power rule becomes 2 when we take its derivative, and then we can throw in the point that we're interested in, say, where x is equal to 5 into this formula, and 2 into 2 cross 2 times 5 is equal to 10, which means that the slope of this curve y equals x squared at the point where x is equal to 5 is 10. That's what the slope is there. So let's now do the same things we did manually in the PyTorch library first. So okay, let me connect. Okay, so we import PyTorch, and then we will create a scalar tensor to store this value x. Okay. Also, if you're thinking about why I'm using float number, I just let me tell you this small piece of important information, that many PyTorch function works properly if we have float type tensors. Okay, So that's why I'm being sure to include a decimal place here and get that float type scalar tensor x, and we can have a look at it here. Look, yes. Now the new thing that we are going to do, something that we haven't seen yet in this machine learning foundation, we're going to require the gradient to be tracked on this particular tensor. So by calling this method, it turns the required grad property of this tensor object from false, the default, to true. And we don't do it by default because it takes up extra memory, but when we want to calculate a derivative with respect to x, then we are going to want to start tracking its gradient as we start to perform up forward pass. If we start perform operations of the variable x on the tensor x, we are going to want to track the gradient. And so the gradient gradient tracking happens contiguously. So any variable that is created as a function of x, any tensor that's created as a result of some operations on x will track the gradients on that new tensor as well. So in this case, we have a very simple equation where it's just y equals to x squared. But when you implement that equation here, the gradient has now been tracked from x all the way through y. So that's our forward pass. And now we can use automatic differentiation by calling the backward method in PyTorch. So you use this tensor that we would like to have. So we use the tensor that you would like to have as the starting point of the derivative. So in this case, dy dx. So we go backward from dy, and we do that here with this backward. What happened? I really don't know what happened here. I don't know. Okay, so where was I? We go backwards from dy. Okay, we go backwards from dy, and then we did that here with this backward method call. This now uses automatic differentiation, so it tracks all the way back through whatever tensors were involved in creating y. And in this case, it's just again a very simple single step equation from x to y, but we could have hundreds of functions in this chain of thousands of functions that would be commonplace in a lot of machine learning algorithms, particularly in deep learning algorithms. So to actually get this gradient, the slope of y with respect to x, we can ask for the grad attribute of the x tensor that we started with. And so if we have multiple inputs, multiple tensors, and that ultimately led to y being being calculated, then you could find out what the slope of y is with respect to each of these variables separately by calling the grad, by asking for this grad attribute on each of whatever those variables are. And in this case, we just have x, and we see that that dy dx. So we can that dy dx, so we going backwards from y dy dx is 10, which is exactly what we calculated by hand. So that's autodiff in PyTorch. And after that we will up next, let's do the same computation in TensorFlow. And now we'll do the same thing in TensorFlow. So we import the TensorFlow library, and then we start off the same way as we did in the PyTorch by initializing a scalar tensor. By initializing a scalar tensor with the same value, of course the same 5 as we had in PyTorch. But from here the similarities end and we do things differently. So in TensorFlow, you start this with statement in which we track the gradient tape, so it doesn't happen group. So it doesn't happen globally like it does in PyTorch, where we track the gradient globally. Instead, we track this gradient simply within this width, within this width, and you just always start off with this gradient taping method. You just always start off the gradient tracking with this gradient tape method, and the convention is to call it t, and within that with statement we use the watch method to say what variables we would like to track the gradients on the same way on the same way that we use the required gradient method to do that, and set the required grad equals to true on the x answers in PyTorch. That's similar. It's analogous to what. So we are going to track the forward pass on that x tensor, and then we pass that x tensor into this simple function y, just like we did in PyTorch. And as our equation says we need to, and that's it. So executing it with statement, and then in order to get the slope of the sum, and then in order to get the slope of some variables with respect to some other variables in TensorFlow, we use this gradient method and we pass in both of the variables that we are interested in. So in this case we are interested in dy dx, and so we pass in y and x in our gradient method, and that spits out for us 10, the same answer that we got in PyTorch, and the same answer that we got when calculating the slope of this curve at point where x is equal to 5 by hand. So for me, PyTorch feels much more intuitive and Pythonic than TensorFlow. It's kind of bizarre way of using Python. It doesn't feel very intuitive to me. It's not that fun like in the way in PyTorch. So that's just my opinion. But anytime where we're differentiating with AutoDiff, we'll typically use PyTorch. Although it's good to exercise in TensorFlow, it will be very exciting for you if you just try. So now we are familiar with what AutoDiff is at a high level, and we know how to carry it out in Python. Now we'll begin putting the pieces together so that we can apply AutoDiff to implement a simple machine learning algorithm. So we will fit a simple regression line. We're going to do that in the regression in PyTorch notebook, but we have got a little bit of theory to cover before we jump to that. We will discuss how to use automatic differentiation within a machine learning loop, through how to represent an equation as a tensor graph and then creating that graph in PyTorch. To do that, we're going to represent the very simple equation y equals to mx plus b. Okay, so we are going to represent this simple equation y equal to mx plus b, where m is the slope line where m is the slope of the line and b is the y-intercept. We're going to represent that line equation as a directed acyclic graph, also known as DAG, or abbreviated as a DAG. We'll talk about DAGs in much more details in the algorithm at these subjects of the machine learning foundation series. Now we're just going to quickly talk about it. So the graph, so this graph, the directed acyclic graph of a line equation consists of nodes. So each of these points in this graph is a node 1, 2, 3, 4, 5, 6, and we have an input node which is x. We have an output node which is y, and we have our params both shown in green, the slope and the y-intercept b. We also have operations acting as nodes. So we have multiplication operations where we'll have multiply m times x, and then we have this addition operation which will add b to the product of m times x. Alright, so those are nodes. So those are our nodes. We call them nodes. Another aspect of a graph in graph theory is that we have edges that connects the nodes. So in this case we have 1, 2, 3, 4, 5 edges, and these are directed edges because they flow in a particular direction. So you can have undirected edges which wouldn't be an arrow at all, or you could have also edges that goes both directions. In this case we have edges that only go in one direction, and the graph as a whole has no cycle, it has no loops, so it is a directed because it has directions, cyclic because it has no loops, and graph because we are representing it as a graph of these tensors. So each of these directed edges are tensors that hold some information. So here it holds that information about x, and here it holds information m, and here it's a tensor that carries the product of x if m times x to this addition operation or node, and then there's a tensor here that holds b, and then finally we have a tensor that gives us our output y. All right, now we have our DAG representation in a simple linear equation. Let's jump into hands-on code demo in regression in PyTorch notebook. In order to create this DAG of our simple line equation in PyTorch. In this notebook, we will use the PyTorch automatic differentiation library to feed a straight line to the data points. So we start off by importing PyTorch as well as matplot library for creating some plots. And we are going to use some made up data that so our x values, our inputs into the line equation are going to be these values that are supposed to represent the dose of drug for treating Alzheimer's disease. So this is made up, but the y values were created using the equation of a line y equal to mx plus b. And by doing this, we know that what the underlying model parameters to be learned should be. So I use the slope of a negative 0.5 and this y-intercept of 2. So I use this formula right here, which has that m times x for slope, then our y-intercept, then the added random normally distributed noise. That this allows us to simulate a sample error, because in the real world most processes and surgeons and all biological processes like this made up Alzheimer drug examples, we wouldn't have a perfect relationship between x and y. There would be some random noise associated with our observations, and so we are going to learn a lot more about probability distribution, including the normal distribution, as well as a lot more about the random processing subject. For now, you can just trust me, and this method we have here where it has a little bit of reasonable noise, and we have this argument that here that we set to 0 so that our noise is distributed evenly around our line here. And then this argument here is how much noise this is the standard deviation of the, and this argument here is how much noise. So this is the standard deviation of the noise. Again, it's that's a term that we won't cover in details, but just for now, keep remember that it allows us to have differing amounts of noise. So if you were to make this number large, or if you were to make this number larger for the standard deviation argument, you would add more noise. If you brought it down to 0, then you would have no noise or whatsoever, and you would just be fitting the line. Alright, so I'm not going to run this, or maybe I should. Okay, so let's run this. You can run this code, you can play around, but actually I'm just going to leave it here as it is. I'm going to use some y values that I already created earlier using these functions. So this way for reproducibility of this demo, so that you have and I have the exact same y values, and every time you do or I run this netbook, we have the same y values. I'm just going to use this fixed y values, but again you are welcome to create your y values instead. So following along with my made up Alzheimer's disease example, where our input into the model is the dosage of a drug that we have developed for treatment Alzheimer's disease, and then the outcome that we are measuring, the output of the model is the patient's forgetfulness. So let's have a look at the relationship between x and y according them. Okay, so let's have a look at the relationship between x and y by plotting them out. So you're plotting a scatter plot, scatter plot here with our drug doses along with the x-axis and our parents' forgetfulness. These are the drug doses along the x-axis and the forgetfulness is y. And there are some labels to keep track, but as you can see, there is a clear negative relationship between these two variables. So as we increase the drug doses of our made up Alzheimer's drug, we see that our patient's forgetfulness goes down. So that's where the commonalities between the we're going to use machine learning ultimately with calculus at the core, allowing us to so en route to following the machine learning approach to fitting a line to these data points, we need to initialize our variables or parameters for the line with some random values. So that's a common thing that we do in machine learning. It feels a bit weird if you don't come from machine learning background, but it's very common in machine learning models, from the simplest kind of models like regression model, like fitting a line through the data points, all the way through the most complex regression models like deep learning models. In all of those, the standard is to initialize your model parameters with random near zero values at the start. And as you get to approaches like deep learning, there are relatively sophisticated approaches for selecting random values from a specific distribution that is specific to different parts of in deep learning algorithm. But for our purpose here, for fitting the simple regression model, you could pick any near zero values as your starting point. So I'm starting with 0.9. This is a random value, pretty close to zero. so that it fits our criteria for picking a random initial value for our parameters. Now you might ask yourself, but look at this, we can see there is a negative slope, so why don't you start with a value, a negative value that maybe approximates this here. And well, the instance, I don't want to cheat like that, so in this simplest demo where we just have two variables and we're fitting a line to the points represented by these two variables, we could guess an approximate correct parameter value to start with. So we could pick a slope value that's approximately the slope. We could pick a y-intercept that is very close to 2. We can see that there would be a line here, and that would be, and that would be a step around 2 on the x-axis. So we could guess approximately correct parameters values to start with, or like we did in the linear algebra to subject. We could use a statistical approach. For example, we could use ordinary least square regression to fit inline this data. Then that would, for the simple problem, solve from the parameter very quickly. However, everything that we're doing here, this tiny machine learning demo that we're doing in this notebook, is regression PyTorch with just 2 parameters, m and b, the slope, y and y-intercept, and there's 8 data points. This approach that we're doing in this small scale here scales to models that have millions of parameters instead of just 2, and millions of data points or billions of data points. I mean, this approach that we're introducing in this notebook, this machine learning approach, scales to any size of model, any amount of data. Whereas the other approaches that we talked about, just now guessing what the parameters should be, or linear algebra or statistics, they do not come close to scaling in this way. Anyways, that was I talked a lot to justify my use of that was a lot of talks for me to justify my use of this random 0.9 values of our slope is our starting point. As our starting point, you can pick another random value near 0. You could pick 0 itself, or 0.1 or 0.0.1 or whatever, just as long as it's not too big of a number. The bigger the number gets, the you might make it impossible for your machine learning model to fit. But as long as it's relatively near 0 value, your model should make its way to correct answer to a well-fitting line for the data points. If you do want to get the exact same output as me, and if you're running through this, especially if you're the first timer, I recommend leaving it to the same values as I'm using. And as we saw when we learned how to perform automatic differentiation in PyTorch, we use this requires grad method on our scalar tensor here to set the requirement argument the true, requires grad to true. So this means that now we use our x values and we flow them through a function, and any of the tensors that m tensor comes into contact with also track gradients. And this will allow us to perform differentiation back from our outcomes from our y variable in our line model. And so we'll be able to find the slope of y with respect to m and with respect to b, because when we initialize our y-intercept for the parameter b, we're also going to require gradient tracking. And we're also going to require the gradient tracking. And again, here I'm picking up another near 0 value. When I I when I picked this random values, I picked ones where I knew the model was going to when I picked this random values, I picked ones where I knew that the model was going to have to do some work. So as I mentioned, you can see that the y-intercept is about 2. And so I picked a y-intercept that is close to 0, a very close to 0. And you can see visually that we have negative slope, so I could provide a negative slope for m to make our life very easy for a machine learning model. But I didn't want it to make it too easy. I wanted you to be able to see the model learning and improve over time. And so I picked a positive slope, knowing that yeah, we would be able to see our slope change from positive to negative and gradually fit the data point. Okay, so I created this regression plot function. I'm not going to dig into the details on. You can do it on this. You can do that on your own time. Essentially, what we're going to do here is we are passing in all of our relevant variables. So our x values or our y values are parameters and then we're plotting x and y against each other, as we did here. But now we are also going to use this code here to fit a line to the database on the m and b params that we have at any given time point. So here we have when randomly initialized m and b with these values, we know don't fit the data well. When you fit a line to it following this code here, the line doesn't so here when we have randomly initialized m and b, knowing that the values that we don't know fit the data very well, when you fit a line into it following this code here, the line doesn't fit very well. Obviously the line does not fit the data very well. So what we're going to learn next is how to fit this line to the data using machine learning. So we'll learn how to fit this next line using machine learning. We have a method that actually allows us to take all of the components of our graph. This is the regression. So remember, we have this computational graph. We have our x values, we have y values. We initialize this at the top of this. We initialized this at the top of our notebook, and then most recently we initialized our parameter with subquad and quad random starting values. We have all the components of our graph, and now we can link them together with this regression with this regression method that I created, which takes m and x and b. So it takes our parameters, it takes our input, and it multiplies m times x, adds b, which will give us y. So that's So there we have queued up everything up. In the next video we will learn a little bit more about machine learning theory, and then we'll come back right into this regression and PyTorch and use that machine learning theory to actually fit this line to the data points, thanks to automatic differentiation. Bye bye.